Hello, I'm Shomik, and I'll be presenting our work, Complex Valued Fourier Primal-Dual, Undersampled MRI Reconstruction in Hybrid Space. I have no financial interest to declare. Magnetic resonance imaging suffers from slow acquisition speed. The speed of acquisition can be increased using undersampling, but that can result in loss of resolution or might also introduce artifacts. Several deep learning-based approaches have been proposed over the years to improve the image quality of undersampled MRIs, working in the image space, K-space, or in a hybrid space of both image and K-space. However, most of these approaches treat complex-valued input as two separate real-valued data by splitting the complex data into real and imaginary parts and concatenating them on the channel dimension, discarding the rich algebraic structure of the complex data. This research proposes complex-valued neural networks to perform undersampled MRI reconstruction in hybrid space. So what is complex-valued convolution? We all know the real-valued convolution operation where the convolution kernel W is convolved over the input X to obtain the output S. In the case of complex-valued convolution, the kernels have real and imaginary parts so as the input. The real valued part of the output is obtained by convolving the imaginary part of the input with the imaginary part of the kernel, and that is subtracted from the output of the convolution of the real parts. On the other hand, the imaginary part of the output is obtained by cross-convolving the real and imaginary parts and then adding them up. This simulates the underlying complex arithmetic using real-valued entities to perform the equivalent of a traditional real-valued convolution in the complex domain. For this purpose, we have developed the pytorch-complex Python package, which is a wrapper over the PyTorch framework. This can be used as a drop-in replacement for the PyTorch layers like convolution layers or linear layers by simply replacing the import as shown here. This package also provides several complex-valued activation functions. In a separate study presented at the IEEE IPASS 2022, we demonstrated the benefits of using complex-valued convolutions over the traditional real-valued ones in the medical imaging domain. We have proposed two different network architectures here, Fourier-PDUNet and Fourier-PDUNet. The Fourier-PDUNet is a modified version of the Primal-Dual model proposed by Adler and Octon for computed tomography reconstruction, while the Fourier-PDUNet is proposed by modifying the PDUNet model that was originally proposed for computed tomography and radial MRI reconstruction. We have employed the fast Fourier transform and the inverse fast Fourier transform instead of radon and inverse radon transforms applied in those previously proposed models. These models can be considered as unrolled iterative reconstructions. The dual blocks try to predict the missing parts of the K-space, while the primal blocks attempt to remove artifacts in the image. The undersampled K-space G is first supplied to the initial dual block of the models along with the two initial states H0 and F0. The output of the first dual block is provided as an input to the first primal block along with F0. It's worth mentioning that the initial state F0 in case of the Fourier-PDUNet is all zeros, while in case of Fourier-PDUNet, it's the undersampled image. Afterwards, the output of the first primal block goes as an input of the second dual block, along with the undersampled K-space and the output of the first dual block. When the data goes from the primal to dual block, FFT is applied, while IFFT is applied when the data goes from the dual block to the primal block. This is repeated for 10 sets of primal and dual blocks. Each of the dual blocks of both the models contains 3 complex-valued convolution layers and 2 complex ReLU activation functions. The primal blocks of the Fourier-PDUNet contain 3 convolutions and 2 preLU activations. On the other hand, each primal block of the Fourier-PDUNet is a unit. The output of the final primal block is the final output of the network. To evaluate the proposed method, we use the T2-weighted axial brain scans from the fast MRI dataset acquired at 3 Tesla with 16 coils. We combine the coils by bringing the K-space into the corresponding complex-valued image space and then applying root sum of squares as a pre-processing step. The fully sampled K-spaces were then retrospectively undersampled using one-dimensional variable density sampling with acceleration factors 8 and 16. We trained our models using the L1 loss, which was optimized using the atom optimizer for 50 epochs, with an initial learning rate of 0.001, which was decayed by 10 after 25 epochs. To benchmark our results, we have used a full image space model ReconstructNet as our baseline. Now let's have a look at the results quantitatively using SSIM, NRMSC, PSNR, and UQI. It can be observed that both the Fourier models outperform the ReconstructNet, while Fourier-PDUNet performed the best among the three for both acceleration factors. Let's have a look at qualitative comparisons. The results and the corresponding SSIM maps are very similar for all three models. However, we can observe that Fourier-PDUNet results show fewer deviations from the ground truth. Now to conclude, we propose two complex-valued models working in the hybrid space of K-space and image space, Fourier-PDNet and Fourier-PDUNet. Fourier-PDUNet achieved statistically significant improvements over both Fourier-PD and ReconstructNet models, resulting in 93% and 92% SSIMs for acceleration factors 8 and 16. In the future, we will compare the proposed models against other state-of-the-art models and also evaluate their clinical applicability, including applying to phase-sensitive data like MR thermometry. Moreover, we plan to extend these models to 3D. The code of this research is publicly available on GitHub as a part of the NCC 1701 repository. Thank you so much for your attention and looking forward to your questions and feedback.